Assalamualaikum dan salam sejahtera. Today, I would like to introduce to you another method that we could use to calculate or to predict the flow rate for pipe network. So this method called the quantity balance method. So this method is actually to determine the flow rate for each pipe. For example, we have these two input pipe and one output pipe. So we need to estimate what is the flow rate for each pipes. So the calculation is done by using the idea of head losses. Okay, because as I said, we could balance the head losses here, whether we calculate it clockwise or counterclockwise, or we calculate it, we compare between the input and the output. So the same idea is written here. So if our first estimation is not correct, what we need to do is we need to change, we need to take a little bit, we reduce the amount of flow rate from the greater one, and then we top up, we add to the lower one. So idea dia sama sahaja, iaitu kita akan cuba balancekan, kita akan cuba imbangkan jumlah kadar alih. Kerana kadar alih kita percaya ia mesti memenuhi conservation of mass ataupun kita kata memenuhi continuity equation. So the continuity equation must be fulfilled. For example, we have one situation like this. So the total input, which is A to B and C to B, must be equal to the total output, which is B to D here. Okay, so from the continuity equation, we can write this equation. Flow rate from A to B plus flow rate from C to B must be equal to the total output, which is the flow rate from B to D. Okay, you could see from this diagram here. So, and then this is the equation of continuity equation. And then from our previous calculation, previous lesson, we know that the head loss is now can be calculated by using KQ square. And we could derive this term to Q. So we have DHF over DQ, it will become 2K and Q. And then we rearrange, we bring the dq here to the right hand side. So we have df equal to kq dq. So and then we could also rearrange this term to be written as k equal hf over q square. So and then we substitute these two ideas. We substitute the value of k here with this term, and finally we could get this term. So and then we again rearrange the value of dq here to the left hand side, and then we could write as q over 2hf times df. So and then this is the equation from our continuity equation. What we need to do is, okay, we assume that our first assumption is not correct. So what we need to do is we need to take a little bit from the input. We have two input here, so we need to take a little bit, some portion from the input, and then we need to add into the output here. So it is a little bit different compared with Hardy-Cross method, because in Hardy-Cross method, we just take one difference of delta Q. But for this method, we assume that might be we need to take a certain amount from A to B, but the amount that we need to take from C to B, it might be different to the amount of A and B. So means that you need to deduct with delta QAB, and at this portion, you need to deduct with delta QCB. So means that the amount that you take from the input here is different. Then this both value, QAB and QCB, then these two amount will be added to the output. Means that the amount that you add to the output here is the summation of these two amounts. So we could write it as dqbd. So please be alert that we don't just neglect minus with delta Q, and add with delta Q, because you know that the total flow rate must be equal. So we need to add these two value and become this term. So it is safe for you just to write the dqab, dqcb, and dqbd. So and then from this one, we could rearrange the value into this term. So we have a QAB. So it is equal to, so this is actually comes out from our previous equation of this one. So we have dq equal Q2HF dF. So if the Q is AB, so the Q here is also AB, and the losses is also for the AB root. So we have a 3 delta Q here, dq. So we prepare the 3 items, and then we substitute in this equation number 2, and then we could simplify it as this one. So and then if we rearrange that one, we could write DHF is equal to QAB plus QCB minus QBD equal QAB over 2HF for AB plus QCB over 2HF over CB and QBD over 2HF for BD. So this equation, all of this equation can be simplified as this term. So it is mean that we deduct the total input with the total output, because this is AB and CB is input and BD is output. And then from this one, we could say that we do the summation, we get the summation for all the input and output. So we have the Q over 2HF for inlet plus the total, the sigma for Q over 2HF for the outlet. So what we need to do is we need to calculate this one to make sure that the delta F is equal to 0. So so this is the equation, and again in this method it is same with the Hardy-Cross method. So we don't take the value of DHF as our final equation, final answer. So our final answer should be the prediction of the flow rate. Okay, we see the example. So for example, we have an inlet here with 0.25 meter cube per second. Then we have pipe 1, pipe 2, and pipe 3. So each pipe is now connected with a reservoir like this. And then we take, this is a point A, point B, and point C. We take that the friction coefficient for each pipe is 0.02. And then we assume that this water flows naturally. So the elevation is important. So from this diagram, we know that the elevation for A is 80 meters, elevation for B is 70 meters, and elevation for C is 60 meters. So, but the problem is we don't know what is the flow rate for each pipe. So, because we assume it is flow naturally, because if we assume that there is a pump here, so the inlet can be from anywhere. So, I mean, whether the inlet is from the above the elevation or the inlet is below the elevation or above the elevation, the water can flow because it has pump to increase the energy. So because we assume that it is flow naturally, so we must assume the location of inlet. So because the highest elevation here is 80 meters, so the inlet must be at least higher than 80 meters. Okay, so for this situation, so we assume that the elevation, the altitude for the inlet is equal to 150 meters. Okay, this is first assumption. So you may use your own assumption. Might be 180, might be 200, or might be 100 meters. It's okay. I will show you the calculation whether you need to do the second iteration or not after this. Okay, let's say it is 150 meters. So what we can do is we could write three different Bernoulli equations. So as you know, Bernoulli equation is only valid from inlet to A, from inlet to B, and from inlet to C. Please do not compare your Bernoulli equation with A to B or A to C or C to B, because in reality, the water is not flowing from B to C. So the Bernoulli equation is actually the total energy on the streamline. So you need to understand that. So because if we draw a streamline, we only could draw from the inlet to the point A, inlet to B, and inlet to C. So, and then, for example, if we compare inlet and A here, so we have pressure, velocity, and elevation, Z, and also the losses, HA. So, and then we assume that the pressure, so the inlet here is also from the tank here. So, it's open to the atmospheric pressure. So, the pressure is 0. The velocity is 0 because we take point at the surface level here. And the Z is 150, our first assumption of the elevation of inlet. And then the elevation of A is equal to 80 meters, and we have certain amount of losses. So means if we write three Bernoulli equation for A, B, and C, we could say that the losses of HA is 70 meters, B is 80 meters, and C is 90 meters. So to ease our calculation by using this previous mentioned equation, what I propose here is you do your table here. So we have pipe 1, pipe 2, pipe 3, and then we have the value of K. So you could calculate the value of K by okay, so you have the value of, okay, I'm sorry, the value. So you could calculate the value of K here. So I will give you, might be in this question, I forgot to give you the value of length and the diameter of the pipe. So in proper question, you will have the value of F, and then you have the value of L and the value of D. Then you could calculate the value of K. So let's assume that for each pipe, we have the value of K as this one, 10,326, 12,000, and 50,000. So, and then this is the value of HF. So we calculated previously, and we show as HA, HB, and HC. So we put it here, 70, 80, and 90. And then we could calculate the value of Q, which is the HA over K, square root here, and then we could calculate this one, and also we could calculate the Q over 2 HA as this one. So, and then, so for this situation, we need to assume that the Q in over 2H for inlet is equal to 0, because if we put the calculation here, so we are comparing inlet with inlet. So the elevation is 150 and also 150 here. So the losses will be 0. So we assume that Q in over 2H for inlet is equal to 0. Then we substitute all that value in this equation. So we have a sigma Q, total flow rate for inlet, minus total flow rate for outlet. And then we divide with the Q in over 2HF for in plus Q out over 2HF over out. So the best one is we get the delta HF is equal to 0, because the idea is to get delta DHF equal to 0, we need to get the upper terms here is equal to 0. So mean when the upper term is balanced, Q in is equal to Q out, so you get the delta HF is equal to 0 means your estimation about the flow rate is correct. Okay, so because we did our first assumption, so the Q in here is given in the question, so it is 0.25. So and then we minus with each output, so we have 3 output there, so we minus with 3 output, and then we divide with the total value of Q in over 2 H in. So in this situation, as I mentioned previously, Q in over 2 H in is equal to 0, because the calculation is 150 minus 150, so you will get 0. So we neglect the value actually. So after we calculate this one, it is equal to 8.67 meters. So means that the losses is unbalanced. So what we need to do with this one? So this actually, okay, if we see the calculation here, so we found that the losses here is actually closely related to the elevation. So we just minus the value of elevation here to get the value of losses here. So and then what we do with our 8.67 meters here, because it is reflect to DHF, so the sign is plus here, so we plus with our first assumption. So 150 plus 8.67, so it's become 158.67 meters. So this is the new elevation of point J. Okay. I'm sorry, it's not a point J. This is the elevation here. Okay, this is the elevation here, not point J. So it is 158.67 meters. So and then what you need to do is you need to verify your answer for the second time. So this is the confirmation of calculation. What you need is you need to calculate again using the same idea, but you need to use the height of 158.67. So for example, we have pipe 1, pipe 2, and pipe 3. So and then we have the value of K. So the value of K is remain constant. So it's not change whether the height is different. So and then the assumed HF is 158.67 minus 80. So you will have 78.67, 88, and 98. So in this calculation, please be accurate with the decimal point, because it will give you a big change actually if you neglect the value of decimal point, the value here. So and then this is your new K. So and then this is the value of Q over 2HA. So and then what we need to do is we substitute in the equation, and finally we get delta DHF is equal to 0 meters. So now it is assumed that we successful balance the losses between we get 0 losses, so we are successful to balance the flow rate at outlet and inlet. So what is our final answer? So our final answer is actually this value. Now you could mention in your diagram that for pipe 1, the flow rate is 0.087. The pipe 2 is 0.083, and for pipe 3, the flow rate is 0.08. So it is good for you to recheck the value here, because the inlet is 0.25 meter cube per second. So the outlet also must be 0.25. So if you add all of these, so you have 7, 3 is 0. So you have 8 times 3 is 24 plus 1. So you get 0.25 meter cube per second. So it is good for you to balance this number, because sometimes when your decimal point is very long, so you will get this number. It's still not exactly the same with the inlet. So it is good for you to recheck this value. Okay, now mean after you do the confirmation of calculation, you will find that the delta HF is equal to 0. Then this is your final flow rate. Okay, let's say for the tutorial 2 here, so we start with the same question, but I would like to show you what happened if we assume the height is actually 200 meters. Okay, so the 200 meters here, so means that you could calculate the delta HF is equal is minus 45.3. So this is I shortcut the calculation. Okay, the value, this one, delta HF here is the value at this stage. So mean that you need to calculate here. First, you need to imagine that the inlet here is 200 meters. So, and then you need to subtract with 80 meters here. Then you could have this this kind of table. So this table, so however the value here is 120, 130 and 140. Okay, so okay, please be alert of this one. So you need to redo this calculation. Okay, and then you substitute in this equation, and finally you will get the value of the HF here is equal to minus 45.3 meters. Okay, so and then because the sign here is minus, so what we need to do is we subtract with the first assumption value. So our 200 minus 45.3, so we get 44.7 meters. Okay, then here this is not the final answer. Okay, because we are calculating, we are predicting the flow rate. So what you need to do is you need to do the confirmation of calculation. So this calculation is actually in this table. So means that we know that the inlet here is 154.7. So you need to recalculate the value of HF by replacing this one is 154.7 minus 80, 70 and 60. So you get the value. So now you could calculate the new Q here. Okay, I'm sorry here, this is not HA, actually this is the HF. So for pipe 1, you just use the HA, pipe 2 is the HB, and the pipe 3 here is the HC. So this is also a typo here. So you need to do your confirmation of calculation by replacing this value with the 154.7 meter. And then after you do the calculation using this value, you will find that the delta HF is again not equal to 4.1. Then, so because the sign here is plus, so what you need to do is you need to plus to the value that we get previously. So we get 154.7. We plus with 4.1, and then we get 158.8 meters. So actually, after you get this one, you need to do again the calculation of this one. So you need to back to the first calculation of this one. So you need to assume that the height is 158.67. You do that one, and finally you will get a very small value to be deduct or to be add here until it achieve this is the best answer. So it is 158.67. So it is about 158.8. So might be you need to deduct at certain value to get the accurate value. Okay, because at this situation, I think the delta F is still shows some very small amount.